Welcome to the last lecture of week 4. So, we have already discussed about MIPS implementation. So, we will continue with that and we will end the week 4 lecture here. So, the data path design of MIPS. So, individually we have seen that how we are actually executing a particular instruction. For executing a particular instruction, what are the micro operations that are required to be executed. Now, for doing so, how the data path is actually designed, we will see here. So, we now show the data path for the 5 steps as mentioned for executing MIPS 32 instructions. And we are assuming here that there will be no pipelining. This is also known as single cycle implementation. Only after one instruction is finished can the next instruction start. Single cycle implementation, by this what we mean is that we execute one instruction fully and then we move to the next instruction, and again we move to the next instruction after executing the previous one. Later we shall extend the data path of pipeline implementation. We will discuss various pipelining issues related to the techniques for faster execution of instruction in later phase of this particular course. Now, let us see how the data path will be for the various stages. First, taking into consideration the instruction fetch stage. So, in the instruction fetch stage, from the memory MIPS, the location content of the PC pointed by the PC, we will fetch the data and we will be putting it in IR. At the same time, PC will be incremented by 4 and it will be stored in NPC. So, for doing so, we require a 32-bit PC, 32-bit NPC, a 32-bit instruction register, and of course a 32-bit adder. So, now we see that from memory this PC will hit the instruction memory. PC contains the address of the next instruction to be executed. So, it will hit the instruction memory and the data will be available in IR. And this PC is added with a constant 4 and this is stored in NPC. So, these two operations can be performed using the following data path that is there. So, the PC is hitting the instruction memory. From instruction memory in the IR, the instruction is available, and from PC it goes to the ALU for incrementing, which is stored in NPC. Next, move on with the ID stage. So, in the ID stage, what we said, we decode that instruction, and after decoding that instruction, we also fetch the particular fields, that is the registers which are source register, the destination register, the immediate field, etc., and we make it available for that particular instruction execution. So, from the register bank, this RS, RT and RD from IR it is coming, and from this register bank it is going to A, B, and after sign extension it is going to the immediate. So, in A, one of the source register value is coming depending on the instruction. In B, another source register value is coming, that is RT. In IMM, this IR, the immediate value from IR, which is sign extended to make it 32-bit, is stored in IMM. It is sign extended and it is put in IMM. IMM1 calculation is not shown, so it is pretty similar. Now let us see what happens in the execute stage. So we are looking here step by step, fetch, decode, then execute. And for execute, how my data path will be. So for the execution, we know that there can be various kinds of operations that can be present. One can be memory reference, another can be register ALU instruction, register immediate ALU instruction, and one can be branch instruction. So for all these kinds of instruction, we see that this particular data path will be sufficient. Let us see how. So we need to add and with A the immediate value. So there is a mux which is attached to this ALU. ALU is having two inputs, and in this ALU one is coming from NPC, another is coming from A. So depending on the select line, this can be taken care, which input will go in. So for memory reference, A will come in, accordingly the select line will get activated, and immediate value will be coming. So accordingly the select line will get activated and the immediate value will come from here to ALU. So here we can see that A and B is coming from these two mux, and along with B that immediate value can also come in here, and which is available after ALU operation. The ALU output is available at ALU out. So we are doing this operation and putting it in ALU out. So 32-bit ALU out, 1 bit cond is required for condition checking, and 32-bit 2x1 mux is also required. Now let us see for others, register ALU operation. So if it is a register, then A input should go and B input should go. In that case, the select line will be selected and A input will go to one input of ALU and B input will go to another input of ALU, and the operation will get performed. Similarly, for register immediate ALU operation, A will come in from the first multiplexer to the one of the input of ALU, and IMM will come from another multiplexer and will go into the next input of the ALU. And for branch, what happens? The NPC value must be added with the immediate value by shifting it to left 2 position. So in that case, from this mux NPC value will come in, and from this mux this IMM value will go in, and the operation will be performed. Similarly, for the cond will be operated with, this cond will be available based on this A operation 0. So A will be operated with 0. So A input is coming, will be checked with 0 and the condition will be outputted here. So all these operations are actually performed in the execute stage using the following data path. Let us move on. MEM stage. In the MEM stage, what basically happens, which all instruction will require memory? Load operation, store operation, branch operation, and for all other operation, NPC is stored in PC in this particular MEM stage. So let us see the data path for MEM stage. So the data path for MEM stage, in this stage what happens that this is the data memory from where we will fetch the data. Now we know that if we need to read it from a particular location, we need to put that address in the MDR basically, and then we hit the data memory. In this case, what is happening? This from ALU out, because sometime for immediate data operation, we have seen that an immediate value is added with some register value, and then that is available in ALU out, and then that ALU out is put it in the memory data memory, and it is fetched from there. So, in this case, ALU output will be put in to the data memory, and then the value will be read, and which can be stored in LMD. So, for the load operation, this happens where memory location pointed by ALU out is read and it is stored in LMD. And in all cases, we can see that PC is the NPC value, the updated value of PC is also put into updated value of PC is, which is stored in NPC, is stored in PC. So, similarly, all other operation can be taken care using this particular data path, Let us move on with the write back stage. In the write back stage, what happens? We write the value into the register. So, finally, whatever value, either that value is coming from the ALU output or the value is coming from memory, it should be written back into the destination register. So, in some cases it is RD is the destination register, and in some instruction RT is the destination register. So, accordingly, for register ALU operation, this ALU output is stored in RD. For register immediate ALU operation, ALU out is stored in RT, and for load instruction, the LMD value, because the data which is read from the memory is stored in RT. So, this is how it can be done. It can be selected from the mux either from LMD or from ALU out. Now, that till now we have seen that the various data path that is required in the various stages in instruction fetch, instruction decode, execute, memory operation and write back. So, in 5 stages we can see that what is the data path that is required in MIPS. Now, let us put it together all. So, whatever we have discussed till now, starting from instruction fetch to instruction decode, then to execute, and then to memory operation, and finally to write back. So, whatever we have seen starting from fetch to write back, all are now put in together. So, this overall picture gives you an idea that how it is actually happening. This is the data path which is there for MIPS. So, here initially the PC hits the instruction memory, value of PC is hit to the instruction memory, the instruction is read and stored in IR. After it is stored in IR, the instruction needs to be decoded. At the same time, when it gets decoded, then from various registers, the sum of the other register gets populated, that is A, B, IMM, etc. And next we execute it. After decoding, we execute it. For execution, it is required that we get the data from A and B or from an immediate value. Accordingly, mux are in place to select any one of the value out of the two. which is fed to the ALU, and from ALU we are getting ALU out. Now, once the data is available in ALU out, it is sometime again required to get the data from memory. So, in that case, it is again hit to the data memory and the data is read and it is stored in a register known as LMD. And finally, from LMD, it is written to the register bank in the write back step. So, all the steps step by step that we have seen in bits and pieces in previous slides, here we have put it all together, and by one step, by it is now we can see that how step by step this is performed. So, this is the overall picture. Now, what is the simplicity of the control unit design here? You see that there is a regular structure here. That means all the instruction we know are of fixed length. We know that this particular field is for this particular register, that is source or destination. This is an immediate field, and so on and so forth. So, we actually understand that for in MIPS the instructions are very regular, the structure is same. So, all the instruction will be pretty much not pretty much, it will be exactly same. Depending on what kind of instruction, it is a load or store, some values will differ. Otherwise, it is very same. So, because of this, due to the regularity in instruction encoding and simplicity of instruction set, the design of control unit becomes very easy. So, we can see that the control unit that is designed, that is the data path which is there, it is very easily can be made. So, control signals in the data path are load PC, load NPC, read IM, load IR, read reg port 1, read reg port 2, load A, load B, load IMM, mux ALU 1, mux ALU 2, ALU func, load ALU out, mux PC, read DM, write DM, that is read data memory, write data memory, load LMD, mux WB, write reg finally. So, using these control signals in the data path, we can generate all the control signals for any instruction. Now, let us see this control signals for some of the instruction. You recall our discussion of this week for single bus architecture. We have seen that how corresponding to their data path, the control signals are generated and how we can execute it. Similarly, here also we have shown that these are the control signals available for MIPS. Now, I will show you that how a particular instruction get executed using those control signals. Now, add R2, R5, R10. So, here we fetch the instruction, read instruction memory, load IR, and then load NPC. So, in the first fetch step, these particular control signals are activated, that is read instruction memory, load IR instruction register, load NPC. Now, after doing so, in the next step, we are loading read reg port 1, read reg port 2. After reading from here, load it to A and load it to B. That is the decode phase. At this phase we are also decoding and we are also fetching the value from the instruction and storing it in A and B. Now we are doing the exact ALU function. So here ALU func will be add, this is add operation. Mux ALU1 will be 0, we need to select A. Mux ALU2 will also be 0, we need to select B. And then after this operation, load ALU out. So ALU out will be loaded with the operation performed, that is add A and B, where A and B will contain R5 and R10. Now here the memory operation performed, this is the mem phase. So in the mem phase, the memory operation is performed, and in this phase we load PC. So PC is loaded with the new value of the NPC. And finally in the write back phase, the output of ALU that was present will be written to R2. In this, mux WV will be set to 1 and write to the register. Write reg will write it into the destination register, the output value of that. So to execute this particular instruction, these are the steps required and these are the micro operation or control signals generated for execution of this instruction. Let us see another instruction, that is load R2 100 R5, that means 100 and R5 will be added, then the value will be read from memory and it will be loaded in R2. So at different phases different things will happen. So let us say this is the fetch phase is standard. In the decode phase, register value of RS will be loaded in A, and of course other values will also get loaded, but here we are showing which are required for us, which are needed for us. So IMM will actually store the IR value 0 to 15 bit IR value, and it is sign extended to make it 32 bit. And what we are adding, we have to add this IMM, that is the immediate value, with A, and we have to store it in ALU. So ALU out will have A plus IMM. We add these two values. And finally this NPC will be loaded in PC. Now the content of ALU out will be brought in from memory, that is the data memory, from the data memory, and it will be put up in LMD. After this is done, finally from LMD it will be put into the destination register, will be put in RT, because destination register it sometimes can be RT or RD. So let us see the corresponding control signals. So first we read IM, load IR and load NPC. Similarly here we will read reg port 1, we will load A and we will load IMM, the immediate value. Here ALU function will be add again, mux ALU1 will be A, but now you see mux ALU2 will be 1. Earlier when it was A and B, the mux ALU1 was 0 and mux ALU2 was also 0, but now it will be the immediate value. So in this case mux ALU2 will be 1, the next value will get selected depending on the mux select line, and then we load ALU out. So this will be added and will be loaded in ALU out. Next in the mem phase, of course we will load PC, that will be done for all the instructions, and now this ALU out contains the address from where we have to read the data. So, as this contains the address where to read the data, we will read it from the data memory and we will load it to LMD. So, data is now read from the data memory and loaded in LMD in this particular phase. And finally, we write back. We write back the data into reg RT. So, mux WB will be 0 and we perform write reg. When we perform write reg, the LMD value is loaded in reg RT. So, this is how we can perform the operation load word R2, 100 bracket R5. So, we have come to the end of lecture 22 and of course week 4. So, in this week we have seen how we can design a control unit, the various methods that are present in the design of control unit, and by this time we have also known that typically for MIPS, what is the control unit, how they have designed the control unit. We have generally seen a control unit design and then specifically we have seen in MIPS how it is done. Thank you.